Let's finish up talking about drag forces. So, drag forces can be split into two major components, and this gets accounted for in the drag coefficient. So the drag coefficient is going to have a component for the frictional portion and a component for basically what we call the stagnation or the pressure component. And what that means is if I've got, say, fluid flowing over this tablet here, right? So let's say it's coming across from left to right. And so if I've got fluid moving along, as the fluid moves along, when it hits the surface of this tablet, some of that fluid is going to stick because that fluid has viscosity. It's going to resist flow. All right, so some of that, and we call this the no slip at the wall condition. We've talked about that before, right? If I've got some flat surface here, this pen is just about done. Need to quit grabbing that pen. So if I've got fluid flowing over this surface, right? Well, there's a little area here where there's not much fluid flow. Right, so there's this area right here. We call this the boundary layer. And that's what we're going to talk about today. There's a no slip at the wall condition. So there's molecules stuck right here on this surface. So as I've got fluid flowing along here, there's going to be molecules stuck onto that surface that are not going to move, and that's going to slow down the molecules immediately above them that are flowing over, and then that's going to slow down the molecules in the next layer above them, and so you're going to have kind of this area, this region above the surface where there's very, very slow fluid, and this is what we call the friction portion of the drag. If I've got fluid flowing over this tablet, it's going to cause both a friction force and a pressure force. So the friction force, again, is the flowing over the surface. The pressure portion is where the fluid is moving along, and some of that fluid gets stuck right here, right? So if I've got speed here, at the same elevation I've got no speed. We talked about pitot tubes earlier in the class. We said that when there's a change in speed and there's no change in elevation, that kinetic energy has to go somewhere. Right? Bernoulli's equation says that P over rho plus V squared over 2 plus GZ is a constant. Well, if Z doesn't change from here to here, Z doesn't change, and the speed changes. Here I've got speed, here I've got no speed. So what happens to maintain this constant? You have to increase the pressure. So the pressure portion of the drag is the result of pressure differences around the body, resulting in this change in speed causing a change in pressure within the fluid. And so these two components added together, the pressure component and the friction component, cause the total drag force. Now, the tables for the drag coefficients that we've looked at last time, those don't, very rarely do they actually differentiate between the two and split them up. Most of the time, it just gives you a single drag coefficient, and it doesn't. We do need to understand that that includes both of these components, but it doesn't necessarily differentiate them, and we don't know how much is which. But yeah, the pressure portion is what we call stagnation. Depends on the shape of the body, right? So if I have fluid flowing along and it encounters something like this, right, where I've got fluid now is completely having to change its momentum 180 degrees, this has a much higher pressure force being applied within this bowl as opposed to just a flat surface, as opposed to even, we talked last time, we saw with the rod and the sign that if I've got a rounded surface, it's a lot easier for this fluid to just move around that. I have a much lower pressure point right here, as opposed to a flat surface, and definitely as opposed to, say, a concave surface. Okay, so it's dependent on the shape of the body. And the shape of the body is going to determine how high the drag coefficient is for the pressure portion, which determines how high the pressure component is for the entire drag force. Alright, so at high Reynolds numbers, the friction portion becomes smaller in proportion to the pressure portion. So the higher the Reynolds number, the bigger the contribution of the pressure component is. And you reach a point where the friction component is sometimes negligible in comparison to the pressure component at a higher Reynolds number. Okay, now, but if I've got flow over a long flat surface, and I think I assigned a homework problem or two that are long flat surfaces. If I've got a long flat surface, kind of like as I've drawn here, the tablet's a nice example of that. I've got a narrow profile here, but a really long surface here. And so this is a special case. When I've got fluid flowing parallel, especially parallel to a long flat surface, there's very little pressure. Right? There's very little pressure builds up right here. Much more of the drag force is based on the friction of the fluid trying to flow over this surface. So there's probably there's minimal stagnation point here. There's not as much of a wake back here on the other side of fluids flowing this way, right? And so in the wake, I'm going to have a very low pressure, right? And in the stagnation point, I'm going to have a very high pressure, and the difference in the pressures is going to cause a pretty big drag force. But over a long flat surface, I have minimal stagnation here and not much of a weight back here. So there's not a whole lot of pressure difference between here and here. Therefore, there's not much net drag force difference. So the friction component over long flat surfaces is caused is the major cause of the drag force. In long flat surfaces is the friction component. Right, so I think I'm used to having a smart board here where I say, well, this approach is zero, or it's negligible at least. Okay. Now, so I've got some things on here, and I think I'm gonna. I don't know that. I think I'm best without having a nice smart board to draw on. I think I'm much better suited to just go ahead and draw this on paper. So we've talked about the boundary layer a little bit before. The boundary layer is the region where fluid is slowed when contacting a surface or an object. And what we're saying there is, if I've got, I'll use green here, let's say that I've got, that's a brand new pen. Let's say I've got some kind of surface down here. Okay, and let's define the x direction is left to right, just like we would normally define x direction left to right. And let's define the y direction as the vertical. Pretty standard there. And let's say this is the y, and this is not my origin. Let's say this is a y value of 0 and an x value of 0 right there at this corner of the plate. Okay? Alright, so let's say this is y0 and this is x0. And let's say out here, as y approaches infinity, I'm going to have a speed, right? The average speed of flowing particles. So out here, I've got flow, and particles moving about the same average speed out here. Now, what we find then is that right here, I'm going to draw this. I'm going to say out here, let's draw entire length of the plate. Let's say that my V average is really large out here as we approach infinity in the y direction. Okay? Alright, so right here at the surface, assuming that the speed of the surface is 0, right here at the surface, you're going to have almost no speed. Okay? The particles are going to try to stick to the surface. They're not going to slip. We've got the no slip at the wall condition, and so not much speed right here. You move a little further up in the y direction, and you get particles moving just a little bit faster. Okay? And as you move a little further away, and right here at the leading edge, basically 0 speed, but if you move a little further away in the y direction, the particles start getting a little bit faster. So the further you get away from that surface, the faster the particles become. And you move a far enough distance away and the particles really start picking up speed. Right? And continue to move away and the particles get faster until you reach a point where there's really, you move a far enough distance away in the y direction and the speed of the particles is moving essentially the same as the speed of all the particles above them. Okay, so if we define some things here, let's define a u vector, and the u vector we'll define as the x direction speed of the fluid. As you can see from my terrible graphic here, that u value is going to be a function of the x location and especially the y location. The further we get away from this plate, the higher this goes. It is also going to have some x variation. I haven't really drawn that in here, but that's going to be in the x direction. So I'm going to put an I vector on that. Now, there's some limits on this we can establish. Some limits that u, if I find the u value at any x value but a y value of 0, that's the no slip at the wall condition. So I'm saying out here at y equals 0, the fluid does not have any x direction speed. It really doesn't have much speed at all, but definitely no x direction speed. And we're saying that u, that at any x location, if we get all the way out to a y value of infinity, u is going to match the average speed of all the particles out here. That's what we're saying. Is the further you go up in the y direction, you'll hit a point where you don't notice any difference in the speed anymore. We just start seeing this average speed over and over again. Okay. So here's the thing. I've got a purple pen in here. I don't know. Hopefully not too many of you guys are colorblind. There's this region here that we call the boundary layer. This is what we call the boundary layer. The boundary layer is defined typically as where you get a u value at any x location, and a lot of times we'll use a value here, we'll just call it the del, kind of an inexact differential, d, and at least this text likes to use del to refer to the thickness of the boundary layer. So that del value is going to have different lengths at different x values. That's my alarm. That's when we're going to reach 99% of the average speed. I'm going to pause. We'll pick up back up there. Now I got a few seconds. So the idea is, well, we'll pick back up.